Okay, so let's look at a side view before I start these free body diagrams of the pin at B, the joint at B. So that looks like this, where this is member 1, this is member 2, okay? And then there's an external force acting on the pin. Okay, follow what I'm drawing there. The way that we're going to break this up is we're going to lump the pin in as we're going to call member 1, not only member 1, but also the pin. We're going to treat those as one body. So you can think of this as it's not necessary for the way we're treating it that this is really what's going on, but you can think of it as the pin is part of member 1. Okay. And so when we have to figure out where to apply forces and stuff, here's like what forces are acting on member 1. Well, there's a force from member 2, so that would be the force on 1 by 2. And then on member 1, there's also that 500 Newton force because it's applied to the pin, which is part of member 1. On member 2, there's no 500 Newton force because it's applied to member 1. All there is a force on 2 by 1. So now let's use this to do those free body diagrams. I think really, especially at the beginning when you're trying to make sense out of this stuff, drawing that side view like that can be a pretty helpful thing. Can sort of get you unstuck when you start spinning your wheels. So okay, free body diagram of member 1. At A, there's a reaction force. I'll just call that RA. At B, there's a force on 1 by 2. And there's also a force of 500 newtons. Free body diagram, and the mass, the weight. So acting at the center of this beam is 50 times 9.81, so 490.5. And then the free body diagram of member 2. There's a reaction force RC. There's the force applied to 2 by the pin, and the pin is member 1, so that's F21, which is equal to negative F12. That 500 Newton force isn't acting on 2, it's acting on 1, so that doesn't show up. And then you have the weight of 490.5. That's the way to do it. This is how we do it. That's the way to do it in this class. But here's another, now this is what you were referring to. This is another way you could do it. It just leads to more variables, and that's why we're going to do this. So this just gives more equations and more variables. Okay, I'm going to do this in some other color. orange for caution. So here's a side view of B with the new approach. There's member 1. There's member 2. And there is the pin. So this is member 1. This is member 2, and we'll call this one P. Okay? And then there's a force vector being applied to P. Okay, so a free body diagram of 1. I don't want to do that view. I want to do this view. So we still have this reaction force RA and the weight. And up here, now 1 is not being contacted by 2 anymore because the pin is something separate. You know, these aren't touching each other. So now this force vector is the force on 1 by the pin. And that 500 also isn't touching 1 because it's applied to the pin, which is something else. Free body diagram of member 2. There's the force vector RC. Over here, there's the force vector on 2 by the pin. The 500 doesn't touch 2. 1 doesn't touch 2. And you have the weight force acting down. And now if you're using this approach, you have to do a third free body diagram. That's the pin. That we would treat as a particle. And that has the force vector, the known force vector of 500 in that direction. And it would have the force on the pin by 1, and it would have the force on the pin by 2. So now, with this approach, we have 2, 4, 6, 8 variables, and we'd have 8 equations. We could solve it. With the slightly better approach, where you don't lose any generality, you get 6 equations and 6 variables. So this is the way to do it. But any other questions about that one?
I have a question about the central properties.
Okay.
Take number 4, for example.
Uh-huh.
Because we can choose where we kind of set our
Mhm.
coordinate system, there's different ways of solving those kinds of problems that can seem different, but the end result is going to be the same.
Yeah, the numbers will be different, but they refer to the same physical spot. And so what you want to do when you're doing a centroid problem where you're calculating reaction forces is for your centroid calculation, you want to use the same origin that you're going to use for your reaction force calculations. In the end, the forces will all be the same, even if the numbers can be different throughout the whole problem. And then at the end, the force vectors magically appear the same, as long as the axes are aligned the same way. Question?
Can we just go over only getting the centroid for number 4?
Yeah.
Because I think I might have to find something weird.
That figure is, the lines are a little out of whack, and it makes it a little hard to interpret what I'm getting at, I think. But if you break it up into, you can break it up a couple different ways. let's break it up like this. There's 1, and there's 2. And for this, for that rigid body problem, I would put the origin here, so that's where I'm going to do it for the centroid calculation. And we know that this distance is 0.3. This distance is 0.2. This is 0.1, and this is 0.1. Okay, so for rectangle 1, the area is 0.5 times 0.1, so 0.05. And the centroid is, the x centroid is the middle of this. That is 0.25. You could calculate the y centroid, but in this case you're only calculating the centroid to figure out where to apply the weight force. And since the weight force is vertical, the vertical position doesn't matter at all because you can move it along its line of action. And then for the second one, the area is 0.1 times 0.2. So A2 is equal to 0.02. And the centroid is going in the positive x direction. 0.3 gets you to the left end of that rectangle 2. And then to get to the centroid, you have to go another 0.1. So x2 is equal to 0.4. And then the total centroid is equal to 1 over 0.65 times the area of 1.
0.07. The areas.
Yes, I looked at the wrong thing. The total area is A1 plus A2, so 0.07. And then in parentheses, multiplied by that, you have 0.05 times 0.25 plus 0.02 times 0.4, and that should give it to you. And you could also, you could break it up into this rectangle 1 that has a length of 0.3, and then a rectangle 2 that has a height of 0.2. You know what I mean? You get the same answer. It doesn't matter how you break it up, as long as you break it up in a way that the pieces don't overlap, and it uses up the whole space. Any other questions? Yep. Number 7 on centroids? Okay. Yeah. Okay, so this is a parabolic one, and I don't have those centroid formulas sitting in front of me. So for a half parabola, what did I say the formulas were? Okay, I'm going to get this time. Okay, so this is, what's this, the base? This is B? A. And then this is H. And the centroid, and it's from this direction. 3A over 5. Wait. Oh, over 8, okay. 3a over 8. And then this one goes from the bottom, and that's 3h over 5. Is that right? Okay. So in centroids number 7, the way that we talked about, the orientation that we're using for the definition of the centroids for this semi-parabolic shape is flipped from what it is in the problem, so we have to take that into account. So this distance here, I'm going to put the coordinate system like this. And this distance is what before we called h, right? And that is 5. And this distance is what before we called a, and that's equal to 15,000. So the x centroid is 3a over 8, which is because I switched it, right? Yeah. I'm too stupid to do this. 3. Okay, so x, 3h over 8, right? So, but these mean the same thing as they did here now, right?
X becomes y in that case.
Yeah. 3. Okay, so that's this one. So okay, tell me what to do here.
3h over 5.
3h over 5?
Yeah.
Okay. 3h over 5. And that is 3. And then y bar is 3a over 8. And what's that? 45,000 over 8. That's right, we don't need it. Yep, you're right. Okay. So this centroid location is here, and this distance is 3. Okay, so a free body diagram of the beam. We have a force vector here, call that R, and then we have a reaction moment, because that's a fixed joint, call that MR. And then we have the force coming down there, and I didn't calculate the area of that shape. What's the area formula? What is it? 2AH divided by what? Okay. So the area is 2 times 15,000 times 5 divided by 3. So what is it? 50,000. And that's newtons. So this total force is 50,000. And then it's just a regular rigid body problem. So you can use you can write out the pancake table, pancake artist row for marzipan. I chose this as the origin, so that 50,000 Newton force is at 3, 0. The about point, let's put that down at that fixed joint. So that's at 4, negative 0.2. So the row vector is negative 1, positive 0.2. The force vector is 0, negative 50,000. And so the moment is 50,000. Then that force R, that's at the about point, so 4, negative 0.2. So there's no about point, no row vector. Force vector is
4, 0. If you set that plot point at that point, then the y component would be 0, right?
of the row vector. Is that what you mean? Well,
Of the r.
I put the origin here, so you have to go down 0.2 to get to.
Does that r have mass?
Oh, it does. It says that it has a mass of 1,500 kilograms. So at the midpoint, then, you also have a force going down of 1,500 times 9.81. So that's 14715. Okay, so the force vector R is Rx, Ry. Take the cross product, you get 0 moment. The couple is Mr. And then the weight force is at 2.50. About point is 4, negative 0.2. So the row vector is negative 1.5, positive 0.2. The weight is 0, negative 14,715. And so what do you get for that cross product? $1.5 times 14,715. 207. 20? 22? Okay. 22, 0, 272? 072. Okay. Okay. And then that's everything, right?
I have a question about that shape.
Mm-hmm.
I mean, when I first looked at it, it seemed to me like there should be 2 weld joints, one to the ground and then one in the
Yeah, you could do it that way.
Stress in the body there, like it was for where the wood.
Right, you could do it that way. It would just introduce more. So you could do that as a structure where you had one body like this. And then a force on 1 by 2 and a couple M on 1 by 2. And then a second small piece that had a force on 2 by 1 and a couple on 2 by 1. And then the reactions that we put. And you'd get a system of 6 equations, 6 unknowns, and you'd get the same answer. So this would be R, this would be MR. But yeah, you could solve it that way, but unless the problem is asking for those internal loads, it doesn't really help you, you know. Any other questions about that one?
I had a question for
Well, we're assuming that that doesn't have any thickness. So think of it like, thin like this. And, well, I guess you have to, I just assumed that that's the midpoint. I just was too lazy to write it. If it looks like the midpoint in a problem I draw, it is the midpoint. So that's the answer. So it would be, and since it's a 45-degree angle, you can figure out that, so this triangle here, if this is 45, this height is, this length is 1, so this length is 1. This length is 1.5. And so the center of that, call that C, would be equal to 1.50 plus 0.5. So 2.5. Does that make sense? Any other questions about homework problems?
Would you do the same for the 30-degree angle?
For the 30-degree angle, that's the one where you would just, this angle's 30 degrees. So imagine putting the tail of that vector at the origin of the coordinate system. And then you just want to find the counterclockwise angle from the positive x-axis to the vector. So, and the magnitude's 5,000. So that force vector is just 5,000 times the cosine of negative 30. 5,000 times the sine of negative 30. Oh, for the location? Yeah, you can just keep adding those locations together. So if this is, think of all of these. Well, think of starting here and adding a bunch of vectors together. So you have a vector that goes like this, a vector that goes like this, and a vector that goes like this. So this first vector is 1.50. The second vector is 1, 1. The third one is 1.50, right? Yeah. So 4, 1. Okay. Any other questions? Okay. It's almost break time. Let's go back to this structures problem. Finish this. So this is the structure example from last time. We isolated member 1. And so free body diagram of member 1 had a reaction force, I assume I called that RA, and then up here a force vector on 1 by 2, and also the, was it 500 or 5,000? 500. So 500 Newton force this way. And that 500 Newton force was applied to member 1 because we're lumping the pin in with member 1. And we got our first 3 equations that said So RAX plus F12X was equal to negative 500. The second equation said RAY plus F12Y is equal to 0. And the third equation, did I use A as the about point? So that would be negative 0.866 F12X is equal to positive 433. Is that right? Does that match what you have in your notes?
Negative 0.50 is your about
You put the about point in the middle of this.
What?
I think that's what you did.
The origin in the middle. I did? Oh. So do these match the equations I got last time?
Yeah, plus 0.5 F12Y minus 433.
Plus 0.5.
So the third equation needs.
Oh, yeah. Right. Okay, so this and then plus 0.5 F12Y, and then it's equal to 433? Okay. Okay, so we got these. This is where we were at the end of last time. And then free body diagram for member 2. Down here we have RC. Here we have the force on 2 by 1 because the pin is part of member 1. So that's negative F12. Pancake artist row for marzipan. So yeah, the origin was down here. So the coordinates of that pin B, the pin at the top, are 0, positive 0.866. The about point, let's choose C. So that would be positive 0.50. So the row vector is negative 0.5, positive 0.866. The force vector is negative F12X, negative F12Y. And the cross product is 0.5 F12Y plus 0.866 F12X. And then this force RC is at the about point, so I'm going to just skip all that. We know the row vector is going to be equal to 0. The force is RCX, RCY, and there's no moment. So we have a fourth equation that says negative F12X plus RCX is equal to 0. The fifth equation says negative F12Y plus RCY is equal to 0. And the sixth one says 0.866 F12X plus 0.5 F12Y is equal to 0. And if we solve that system, well, let's do it. Okay, so these are the equations. And then the variables, I'll call these RAX, RAY, RCX, RCY, F12X, F12Y. So equation 1 says we have one RAX and one F12X. And the constant was negative 500. All the rest are zeros. Equation 2, we have one RAY, one F12Y, and everything else is 0. The third equation, negative 0.866 F12X. Positive 0.5 F12Y. And then the constant is positive 433. Damn it. So we have negative F12X, negative 1. RCX, we have 1. Everything else is 0. Then equation 5, F12Y, we have negative 1. RCY, we have 1. Everything else is 0. And equation 6, F12X, we have 0.866. F12Y, we have 0.5. Everything else is 0. Has anyone already solved that while I've been entering these? Could someone solve that anyways? Two people solve it, and your answers need to match. Yes.
Negative 250, 433, negative 433, negative 250, 433.
Sorry, I got lost. So RA
Yeah.
is negative 250,
Yeah.
and then negative 433.
Yep.
Okay.
Next one.
And then RC.
Negative 250 and 433.
Okay.
Negative 250
Okay.
and 433.
And positive 433.
Yep.
Okay, great. So what that says is let's think about the external loads on these objects. At the bottom here at A, we have a force of 250 to the left and a force of 433 down. At the top, on 1, we have a force of 250 this way, a force of 433 this way, Is that it on member 1? It's not, and you can just go back to the free body diagram you drew to enter these back in. Remember, there's also that 500 Newton force this way, which in other words means when you combine, since these are all at the same point, what we really have here is an upward force of 433 and a force to the right of 250. Okay? And then over here, this is negative F12 acting at the top of member 2. So that is a force this way of, no, a force this way of 250, and a downward force of 433. And then at C, we have a force this way of 250. Which one? Above? Or this one? So this is RC, and it's acting, RC is what's acting on this one, so you don't have to make that one negative. So negative 250 and then 433 up. And what that all means, if you combine all these forces, use inverse tangent for the angles, what you get is a force of 500 like that. Putting that into tension. And forces of 500 like that, putting this one into compression. And that's what we got last time, too. How long do you think it took me to come up with numbers for this problem so that those forces worked out perfectly along, you know? It seems unlikely, right?
Yeah.
But actually, there's a whole class of problems that do this, and that's what the simplification for trusses is based on. Okay, so let me bring that up now, and I'll talk about it a little more in detail in a couple days. What are the odds? Well, good, because any two-force body that's in equilibrium, like everything in this class, must have those two force vectors acting equal and opposite That's bad grammar, but and not just that. So any body that's acted on by two force vectors and is in equilibrium, these forces have to be equal and opposite to each other. But in addition to that, those forces have to be parallel to the line between the two force vectors, where those two force vectors are applied. So acting along the line between the points of force application. Okay, so let me just draw a couple pictures to demonstrate this. Okay, so say that this random object has two forces acting on it. what would happen? So first of all, let's figure out that those forces have to be equal and opposite. So we'll say that there's one force vector acting here and one force vector acting here. Say this force is acting in this direction and this force is acting this direction. You know, like, why not? Well, if this is an equilibrium, you know that Newton's second law requires that all the forces add up to 0, right? And so if these aren't equal and opposite, there's no way that Newton's second law can be satisfied for equilibrium, right? So that can't satisfy Newton's second law. So that's the first part of this requirement. And now the second part of this requirement, so okay, let's say take a different two-force body. So then what about this? One force acting like this, and one force equal and opposite acting like this. Why isn't that possible?
No, it's not much line up.
Yeah, so this isn't possible because it can't satisfy the rotational Newton's second law. This is a couple that's going to produce a moment. So it can't satisfy the moment equation. So you must have okay, so there are two possibilities. If you have a force here and a force here, this is the line going between those points where the force is applied. You can have this. That would be compression. Or you can have this. That would be tension.
Can you go back to the second reason?
Yeah.
Is it because that there's no like symmetry?
Well, just imagine this shape sitting on ice, you know, and imagine one person kicking this part in this direction and one kicking this part in the other direction. It's going to spin. Okay, so that's why you can't satisfy rotational Newton's second law with forces like that. The only way that two people could kick this shape on ice and not have it accelerate or spin is to kick it at the same instant in opposite directions, and they can do it towards each other or away from each other. But that's the only possibility. Okay, so now look back at this problem and convince yourself that this structure is a two-force body. Okay? Because there's a whole, like we broke up the forces into a lot of different ones, but look at member 1. There are two places where forces are acting, and so you can think of F12 and this 500 Newton force as really just a single force vector. And this down here is another single force vector. So this is a two-force body. Okay? And those two forces need to be equal and opposite and along that line. And same thing with this one. Those two forces, so those have to be equal and opposite along that line. And so when you have problems like that, you can take advantage of the fact that you know all the force directions. Well, you know plus or minus all the force directions. And that's what lets you come up with this really concise way of calculating problems like that. The downside is there are very specific requirements for a structure to be made out of nothing but two force bodies. You can't have mass. Yeah, that's a pretty big one. You have to be able to neglect the weight, or this is useless. And another thing is you have to have all of the loads applied at the joints. So you couldn't, I guess I didn't draw this problem, but this triangular problem, we had that external load applied at the pin at the top. If I had just applied that load at the middle of one of the members, this method works just as well, the one that we're doing, but you couldn't use that assumption that everything's a two-force member anymore. Yep?
Say, you could have a mass so long as the other force is your normal force, right? If it's like
yeah, but then it can't be a structure. You're right about that.
Yeah,
So,
it's just a single,
right. Yes, you're right about that. So, but in these structures, you always have joints at two ends, and so the weight would be a third force. Yep, you're right. Okay, we're going to just do a few more examples. I'll do an example, then the next time in class, you'll do an example together. Like I said, this is the key section in this class, so we're going to spend some time on this. Okay, let's take a break, come back at quarter after.
Object that had mass, but it was vertical.
Okay, so let's do another one. So let's say that we have a 45, 45, 90 triangle made out of three members. And these are all pin joints. And do we have weight? No, let's ignore the weight. But let's put, apply a force perpendicular to this member of 5,000 newtons. And then it's supported by a roller at the midpoint of this member. The length's most likely 1 meter, because that seems to be my usual way. I guess this length is 1 meter, which means this is 0.7071, and this is 0.7071. Neglect the weights. And we want to know what are the reactions on each body. Each body. Okay. So there are three members in this. How many equations, how many variables are we going to come up with? And how do you know? Yeah, it's a 2D problem, so each body is 3 equations, 3 variables. Well, each body is 3 equations, and if we can solve it, the whole thing needs to have 9 variables. So 9 and 9. 2 of these bodies are not 2 force members, but one is. What's the one that's a 2 force member? The vertical one, yep. So this one, if you want to be clever about it, which we don't yet, you could you could figure out a way to take advantage of what you know about the vertical member to cut down the number of equations a little bit. But we're not going to do that yet. Okay, so let's number these and reference the joints. So I'll call that 1, 2, the diagonal 1, 3, and I'll call this joint A, B, and C. And so joints A and C, there's nothing complicated going on. All that you have is, well, let's just draw them all from the side view. So side views of the joints. So A, first of all. You have member 1 and member 2, and they're connected by a pin. We're going to assume that that pin is part of member 1. So that means that member 1 feels a force from 2, and member 2 feels a force from 1, and there's no other forces going on. So that one's pretty simple. Skip that for a second. That's the more complicated one. Let's look at C from the side. There's member 2. There's member 3, and then there's a pin. So which one do we want to consider the pin, which one do we want to lump the pin in with? 2, because it's the lower numbered one. So it's like that, and so again, it's the same story as at joint A. There's a force on 2 by 3, a force on 3 by 2, and that's all that's going on at the joint. But now at B, there is, let's think of that as being the connection to the wall. And then we have member 1. And then we have member 3 and a pin connecting all of them. So that's the wall. There's 1, there's 3. Which one do we want to consider the pin to be a part of? 1. So it looks something like that. So, so what forces are acting on member, well, what forces are acting on member 3? Yeah, there's just a force on 3 by 1. 3 doesn't feel anything from the wall. See that? They're not in contact. But something different is going on with member 1. There's a force on 1 by 3. And there's also a force on 1 by the wall. Okay, follow that? All right, so let's isolate member 1 first. So free body diagram for member 1. So up here, there's a force on 1 by 3. And notice that these things that I'm putting here you can get directly from this side view of the drawing. So that's why this is a helpful thing to do if you ever, talk yourself around backwards, which is really easy to do, especially at the start. And unfortunately, I have to tell you, it's going to be easy to get yourself turned around backwards when you come back to this stuff after a few months or whatever. And this is a way to get yourself out of the jam. Draw the side view and figure out what's touching what. So, okay, force on 1 by 3, and then there's also a force on 1 by the wall. You can call it that, or you can just call it RB. RBs. And then at A, we can look at this picture, the side view of A, and we see that all there is acting on member 1 is a force on 1 by 2. I didn't choose an origin yet, but let's put it here. Okay, so I'm going to set up the table. If you ever don't need a table, you know, some of these things aren't too hard to calculate without it. You don't have to write it down, but it's just sort of helpful for organization sometimes. Pancake artist row for marzipan. Okay, so the joint A, or this force F12, that's acting where I put the origin. And let's also, and actually, I was going to say let's put the about point at the origin, but let's put the about point up here. There's more unknown forces here. It'll simplify the equations a little bit to put it up here. So I'll make that at the point 0, 0.7071. So the row vector is 0, negative 0.7071. The force vector is F12 x and y. And so the moment is 0.7071 F12x. And then up at the top, that location is 0, 0.7071. Same as the about point, which means the row vector is 0. Let's do F13 first. And you get no moment. And then for RB, you also have a row vector of 0 because that's also at the about point. The force is RBX, RBY, and there's no moment. So your equations, you get a first one that says F12x plus F13x plus RBX is equal to 0. You get a second equation that says F12y plus F13y plus RBY is equal to 0. And you get a third equation that says 0.7071 F12x is equal to 0. So those are the first three equations. And if it was important to cut down the number of equations, we could simplify this a little bit. Here we see that one of these is already equal to 0, but I don't think there's any point in doing that. To me, I just like to come up with the 9 equations, come up with a matrix, and plug it all in. But any way that you can figure out to solve this system is perfectly fine. Okay, now member 2. Over at joint A, we just have a force on 2 by 1. which I'm going to write as negative force on 1 by 2 because we already have that variable defined. And then we have a normal force from that roller. So that's this way. I guess I'll call that N. And then at C, we just have a force on 2 by 3. So negative F12 acts at the origin. Let's also make that the about point. Now we're on a second body, so you can move the about point. You get, with each rigid body, you can choose the about point wherever you want it. You just have to be consistent inside that body.
Choose the same about point.
You could, sure. Yeah, yep. You'd see you get more variables in your equations. You'd still have the same total number of variables and the same total number of equations, but you'd have more of those variables and more of the equations if you did that, because the moments wouldn't go away for... So if you choose the about point to be at a place where you have unknown variables, those unknown force variables don't appear in that moment equation because the row vector is 0. It doesn't really make much difference. It makes much more of a difference if you're solving it by hand, like through substitution or something. So the row vector is 0. Force vector is negative F12x, negative F12y. That's a place where you can make mistakes. You need those negatives to be in there. You're like, oh, we can? Thanks. Now I don't have to study. That's not what I mean. Okay, and then the normal force is at 0.3535, 0. About point is the origin. So the row vector is 0.3535, 0. The force vector is 0, n. So the moment is 0.3535 n. And then the last one, F23, is at 0.70710. About point's origin. So the row vector is 0.70710. The force vector is F23x, F23y. And so the moment is 0.7071 F23y. So Newton's second law gives equations 4 and 5. Equation 4 says negative F12x plus F23x is equal to 0. Equation 5 says negative F12y plus n plus F23y is equal to 0. And the moment equation gives equation 6, 0.3535 n plus 0.7071 F23y is equal to 0. Okay, so I didn't do this at first, but it's probably always worth checking after every set of equations you come up with to see if you can solve the system that you have yet. 6 equations, so how many variables do we have? 2, 4, 6, and 7, 8, 9. So now we have all of our variables. And so in order to be able to solve this, when we isolate member 3, we need to be able to do it with all old variables without defining any new ones. Because if we define any more, we're going to have more than 9 variables. Okay, so free body diagram for 3. This one there wasn't anything complicated going on here. This just has negative F23. And then there's that known force of 5,000 at the midpoint. And now what's going on at joint B? So let's look at this side view. What forces are acting on member 3? There's a force on 3 by 1. Anything from the wall? Nope. So this is just negative F13. Okay, negative F13 acts at the point 0, positive 0.7071. And I guess I'll choose that as the about point. So the row vector is 0. The force is negative F13x, negative F13y, and there's no moment. Then the force negative F23, that's acting at the point positive 0.70710. The about point is 0, positive 0.7071. So the row vector is positive 0.7071, negative 0.7071. Force vector is negative F23x, negative F23y. And the cross product is negative 0.7071 F23y minus 0.7071 F23x. And now the midpoint. What are the coordinates of the midpoint? So you could think of it in terms of that stuff, or the easier way is it's the midpoint of these 2 points, so just average it. So you get 0.3535, 0.3535. About point is 0, positive 0.7071. Row vector is 0.3535, negative 0.3535. The force vector is, this angle is 225 degrees. So that is negative 3535, negative 3535. And if you take that cross product, you should get negative 2,500. I didn't really just calculate that cross product. Can anyone see how I eyeballed that moment?
0.5.
That's right. This force of, so if this is the row vector, this force is perpendicular to the row vector. That length is 0.5, so you just have 0.5 times 5,000, and then it would cause a clockwise rotation, so it's negative. So 0.5 times 5,000. Sometimes you can save a little time with that kind of stuff, but it's not important. Okay, so equation 7 says negative f13x minus f23x minus 35 is equal to 0, so I'm going to write that as equals positive 35. So be careful with that. I sort of skipped a step there. Equation 8 says negative f13y minus f23y. Again, minus 35 is equal to 0, so that's equal to positive 35. And then equation 9 says negative 0.7071 f23x minus 0.7071 f23y minus 2,500 is equal to 0, so I'm going to write this as equal to positive 2,500. We didn't introduce any new variables, so now we have 9 equations for 9 variables. Why don't I just give the answers to this one and one. Okay, so what do we call these things? What are our variables? We have RB, F12, F13, F23, and N. So 2, 4, 6, 8, 9. RB is equal to 35, negative 35. F12 is 0, 35. F13 is negative 35, 0. F23 is 0, negative 35. and N is 7,071. Okay, so you don't get a lot of intuition out of what's going on from just looking at the numbers. You really have to take these and plug them back into the free body diagrams to figure out what's going on. So let's go back to a free body diagram of member 1. That was this one. So there's a force up at B of 35, 35, negative 35, 35. And then there's also the force F12, F1, no, that's, okay, F13 is what we want here. So plus negative 35, 35, 0. And then down here, there's the force vector F12. So that's 0, 35, 35. And we can simplify this because these two forces are acting at the same place. And you get 0, negative 35, 35, 0, positive 35, 35. Or in other words, this is in compression with a total magnitude of 35, 35. And before we started the problem, we identified that as a two-force body, so we knew that that had to be the case. It might have been in tension, it might have been in compression, but it had to be equal and opposite forces along the line between the joints. Any questions about that analysis for member 1? Yep.
On an exam, would you ask us to find whether it's in compression or tension, or would you stop once we found those individual forces?
I don't know. I don't know yet. I haven't thought of that's. By the way, the test tomorrow is not going to have any of this stuff.
Yeah.
No structures, just the only new stuff on it. It's the old stuff, and then centroids and 3D. Yep. Okay, and free body diagram of member 2. Has negative F12, so 0, negative 35, 35. The upward normal force of 70, 71. And then this is the force on 2 by 3. So 0, negative 35, 35. So in other words, this is being bent. Any questions about that one? And then the last one is the diagonal free body diagram of member 3. We have the 5,000 Newton force there. Over here we have negative force on 1 by 2. No, negative force on 1 by 3. So that's 35, 35, 0. And then down here we have the negative force on 2 by 3. So that's 0, 35, 35. And so this one has the force of 5,000 at the center, and then two diagonal forces, well, a horizontal and a vertical, but they're, like if you think of that member as being horizontal, these are both diagonal sort of towards each other, with values of 35, 35.
Why are they diagonal instead of just horizontal?
Well, one's horizontal and one's vertical. I don't know. That diagonal thing, pretend I didn't say that. That doesn't help. But it looks like this. So this member is in a little bit of compression, and it also has that bending thing going on that this one has. Any questions about any of those? All right, that's all.